Similar to how we define Euler paths or circuits, there's another term that we can define that's similar, and we've talked about this briefly earlier when we talked about the traveling salesman problem, so we'll talk about that again in a second. But um, there's another mathematician named Hamilton who described what are called Hamilton paths or circuits. And they're a very similar idea, except here you have the difference between them. An Euler path or circuit, the goal is to travel through a graph touching each edge exactly once. So drawing a simple path or circuit that covers every edge. A Hamilton path or circuit is more interested in touching each vertex exactly once. And of course, depending on the application, you might care more about one or the other, but both are significant. A Hamilton path or circuit is still looking for a simple path or circuit that doesn't reuse edges, but the goal is to touch each vertex exactly once. So the definition of a Hamilton path or circuit is a simple path or circuit in a graph that passes through each vertex exactly once. So it's a simple path, no, it doesn't reuse edges, and passes through each vertex exactly once. Now, it turns out that unlike the Euler question, Euler paths or circuits had a very easy rule to tell whether one existed or not. There's no rule that simple for Hamilton paths or circuits. Mostly you have to just do it by brute force, which makes the problem harder and doesn't have a good solution. But we can still think about what these look like, and there'll be a couple of homework questions where you can look for Hamilton paths or circuits, and they'll be on small enough graphs that you can kind of just do it by brute force, by looking at some specific, just looking at specific paths and looking to see whether they're Hamilton paths or circuits. Just as a side note, there was a puzzle developed around this many years ago called the Koshien Puzzle. The idea was you could build this dodecahedron, a solid with 20 vertices, so 12-sided, think of like a 12-sided die, for instance, has 20 vertices on it. And so there was a game where they would build one of these, and then you had to find a way to touch all of the corners, all the vertices, exactly once, and then return back to where you were. Or you could draw a map of 20 cities, and it's the same problem, right? The same graph that you can do. The game was just the fact that it was this physical three-dimensional object that you could play with and see if you could find a path like this, a Hamilton path or Hamilton circuit in this example. And this is the basis, as we talked about, of the traveling salesman problem. The goal of the traveling salesman problem is to find the shortest possible path that visits each city exactly once. So the traveling salesman problem kind of adds on this extra approach of the shortest possible path, but it starts with a Hamilton path, looking for one that visits each vertex, each city exactly once, and then it adds on the idea of being the shortest path. And the reason this is such a hard problem is that if you try to do it by brute force, you very quickly run into really big numbers. If there are n cities and they're all connected, which they may or may not be, but if they were all connected, there would be n minus 1 factorial possible circuits. And by working with factorials before, we've seen that they grow very, very quickly. So very quickly this problem becomes unmanageable if you try to do it by brute force. There are some ways that you can try to approach the problem. There are ways that you can try to find a short path. You may be able to find a decently short path, but finding the absolute shortest path, there's no general solution to this problem. There's no easy way to either ensure that a Hamilton path or circuit exists or to find them. So these are sometimes called Hamiltonian paths or circuits, or just Hamiltonians. You might see that term elsewhere, but unlike Euler paths and circuits, there's no easy way to ensure that they exist, or if they exist, to find them. It's mostly just by brute force. Although again, there are approaches you can use to find a path or circuit that will work. And we'll look at some of those in the next lecture. We'll talk about what's called the nearest neighbor algorithm, which approaches this problem and finds a short path, but it may or may not be the absolute optimal. So we'll talk about that a little bit later, but this is kind of the setup for it. The term Hamilton path is similar to the one for an Euler path or circuit, but instead of looking to touch each edge exactly once, we're looking to touch each vertex exactly once.